So now we want to talk about covalent bonds, or covalent Lewis structures, how electrons can be shared. Hydrogen and oxygen have the following Lewis structures. Hydrogen has one valence electron, and oxygen has 6 valence electrons. Hydrogen needs to pick up one more valence electron or drop off one more valence electron. Oxygen, on the other hand, needs to pick up 2 valence electrons. In water, hydrogen and oxygen actually share their electrons so that each hydrogen atom gets a duet and the oxygen gets an octet. So what happens is we see these electrons. Hydrogen is going to share its 1 electron with oxygen, and oxygen is going to share 1 electron with hydrogen. And this pair of electrons is actually going to orbit around both the oxygen and the hydrogen. Same thing is going to happen on this side. Oxygen is going to share its 1 electron, or share one of its electrons with hydrogen. Hydrogen is going to share its 1 electron with oxygen. And in this way, those electrons are going to orbit around both the oxygen and the hydrogen. This is what we call a covalent bond. The shared electrons, those that appear in the space between the 2 atoms, count towards the octets of both atoms. Electrons that are shared between 2 atoms are what we call bonding pair electrons. Electrons that are only on one atom are called lone pair or non-bonding electrons. So they're called a lone pair because that pair only belongs to one atom. A bonding pair orbits back and forth or bounces back and forth between both atoms of the molecule. So a bonding pair will orbit back and forth between both, and a lone pair only orbits around that one nucleus or around that one atom. Bonding pair electrons are typically represented by dashes. This shows the connection between those 2 atoms. Remember that each dash is going to represent a pair of shared electrons. So when we see this dash between hydrogen and oxygen, we need to know that this dash represents 2 electrons. Both electrons are orbiting around the hydrogen and the oxygen. So over here, this dash also indicates 2 electrons orbiting around both the oxygen and the hydrogen. Grand total around this oxygen, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons orbiting around our oxygen, and we have 1, 2 electrons around this hydrogen, and 1, 2 electrons around this hydrogen. So we're going to take a quick moment to look at why the halogens form diatomic molecules. So if we look at the Lewis structure for chlorine, we're going to see that chlorine has 7 valence electrons. If 2 chlorine atoms pair together, they can each attain an octet. So if 2 chlorine atoms pair up, we can share a bonding pair of electrons back and forth between both chlorine atoms. This is going to form a single bond between the 2 atoms to form a diatomic molecule. When we examine elemental chlorine, we find that it exists as a diatomic molecule, just as our Lewis theory predicts. The same is going to be true for all of our other halogens that are found in nature. They're going to exist as diatomic molecules. Hydrogen has the Lewis structure has the Lewis structure of a single electron orbiting around its nucleus. When 2 hydrogens share their valence electrons, they're each going to get a duet, or a stable, which is the stable configuration for a hydrogen. So Lewis theory is correct. In nature, elemental hydrogen exists as H2 molecules, where 2 hydrogen atoms bonded together. So we can actually form multiple bonds with our Lewis dot structures. In theory, or in Lewis theory, atoms can share more than 1 electron pair to attain their octet. So we know from chapter 5 that oxygen exists as a diatomic molecule. If we were to pair 2 oxygen atoms together and then try and write a Lewis structure, we wouldn't have enough electrons to give each oxygen an octet. So if each one has 6 electrons and they share a pair between them, we now have 1 atom that has a complete pair, but one atom that only has 6 electrons around it. We're still short a pair of electrons. We can convert a lone pair into an additional bonding pair by moving it into the bonding region. So what we end up with, if we move this lone pair over here as a bonding pair, we end up with 1, 2, 3, 4, 5, 6, 7, 8 electrons orbiting around this atom, and 1, 2, 3, 4, 5, 6, 7, 8 electrons orbiting around this atom. Both atoms have their stable configuration. Both of them have a completed octet, but what we have between them is 2 bonding pairs. Those 2 bonding pairs form what we call a double bond. Keep in mind that when we are looking at a double bond, it represents 4 electrons, or 2 bonding pairs of electrons. Each oxygen atom now has an octet because the additional bonding pair counts towards the octet of both of those oxygen atoms. So let's take a quick look at the Lewis structure of nitrogen gas. How many valence electrons does nitrogen have? Nitrogen has 5 valence electrons. So if we have 2 nitrogen atoms, each with 5 valence electrons, the Lewis structure for N2 would have how many electrons surrounding it? 10. We have 10 electrons to work with. Are either of the nitrogen satisfied with full valence electron shells? No, we're going to have to convert one of those lone pairs into a bonding pair, but then how many do we have? If we have one bonding pair between the 2 of them, this nitrogen has 1, 2, 3, 4, 5, 6, and this one has 1, 2, 3, 4, 5, 6. So 6, we're closer to our, they each had 5, now they each have 6. Is that enough? No. We wish we had 8. So what we're going to do is convert another pair into our, convert another lone pair of electrons into a bond pair of electrons. Both originally have 5, now they each have 7. We're close, but we're not there yet. So what we're going to do is actually convert another pair of another pair of lone electrons into a bonding pair. We had 5, now this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons orbiting around it, and this nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons orbiting around it. So what we have done is shared 3 bonding pairs of electrons in order to satisfy our valence shells. When we do this, we form what is known as a triple bond. When 2 electron pairs are shared between 2 atoms, the resulting bond is what we call a double bond. In general, double bonds are going to be shorter and stronger than single bonds. So, for example, the distance between oxygen nuclei and an oxygen-oxygen double bond is 121 picometers. In a single bond, it's only 148 picometers. So while Lewis theory does correctly predict a double bond for oxygen for O2 properties of oxygen, this problem led to the development of other bonding theories. So they started looking at how triple bonds are even shorter and even stronger than double bonds. The distance between nitrogen nuclei in the nitrogen-nitrogen triple bond is 110 picometers. In a double bond, the distance is 124 picometers. So when we examine nitrogen in nature, we find that it exists as a diatomic molecule with a very, very strong, very short bond between the 2 nitrogen atoms. The bond is so strong that it's difficult to break, making nitrogen gas, or N2, almost completely non-reactive in nature. Alright, so that's it for our discussion of double and triple bonds. Please let me know if you have any questions, comments, or concerns.